Good morning, students. So this is, let's see, let's choose a nice color. I'm giving you guys notes on your 3.2 differentiability launch. Sorry, no stylus this morning, so I don't know if it's going to be even messier. Okay, this is part 2, or continued. Oh, it's awful. Okay, so we've already talked about differentiable functions, and so we know that differentiable means has a derivativable. And we talked about 4 ways in which a function is not differentiable, or at a point, or on an interval. So this example says find all points in the domain of f of x where f is differentiable. So again, if you want to know where it is differentiable, it's often useful to know where it's not differentiable. Okay, so for a, if you think about an absolute value, this function, it's most useful to think graphically for this problem. Okay, so think about, this is the function, the parent graph is absolute value of x, right? But right now we're shifted 6 units to the left. Oh my. We're shifting 6 units to the left and 1 unit up, right? Okay, so what does this graph look like? This graph looks like okay, 6 units to the right, 1 unit up. Okay, that's where our vertex is going to be. And the slope is still 1. And we have, oh my, it's really difficult without a stylus. An absolute value function, okay? I'm really sorry, guys. Okay, so let's do 1, 2, 3, 4, 5, 6. That's 1. Okay. Something like that, right? Is what the absolute value graph looks like. It's supposed to look symmetrical on both sides, okay? So where is it non-differentiable? Well, we have a corner, right? There's a corner at x equals 6, right? Therefore, f of x is not differentiable at x equals 6. And because of my messy writing, I'm not going to take the time to write it, but you would then conclude to answer the question, f of x is continuous on all real numbers, you know, -6, negative infinity, positive infinity, except at x equals 6. Or you could write it in this notation, right? Differentiable from negative infinity to 6 and 6 to positive infinity. Oh. Right? Okay, I'm going to erase that just to make space for the next problem, but that's how you would do it. All right. So the next problem, it might be a little difficult to think of or graph it in your head. So with most of the time with absolute value problems, what is useful to do is break it up into a piecewise function, because an absolute value function actually is a piecewise function, right? The positive half and the negative half. So let's think of it like this. F of x really equals 2 pieces. One piece is what would happen if if x is positive, and the other piece happens if x is negative, right? So let's start with negative, and if x is positive. Okay, if x is positive, then the absolute value sign really doesn't matter. So 3x minus 2x is, well, the absolute value of 2x is just going to be the same as 2x, just like the absolute value of 6 is 6, right? Because the number is positive, the absolute value doesn't do anything. So 3x minus 2x is just x. Okay? What if 2x is actually if x is actually a negative value, then 2x is going to be a negative value, and the absolute value of 2x is going to get positivized. It's going to get actually you're going to get the opposite of 2x because it's going to go from negative to positive. So it's really going to be 3x minus negative 2x, which is going to be 5x. Okay? Think about it. Take some numbers, plug them in, and see how actually if x is negative, then we're going to have 3x minus the opposite of 2x, which means 3x plus 2x, or we're going to get 5x. So now we could think of it graphically. You might be wondering why I'm using graphing paper but not using the grids on the graph paper. And I'm wondering the same thing about myself. All right, so when x is positive, we have the line x. Okay, and when x is negative, we have 5x, so like a different slope, huh? Okay, so what happens at x equals 0? There's a corner there, right? And this time I'm just saying the point, not just x value. Therefore, not differentiable. I'm kind of being sparse here with my language. Not differentiable at x equals 0. And so, again, I'm just going to do this. You would say that f is differentiable everywhere except at x equals 0, or you could use the interval notation. All right? Going on. Now this is important. By the way, there's a lot of important stuff in the book that we're not going to go over in these notes, so make sure you read the book. Make sure you notice all the little graphs and notes about local linearity, the intermediate value theorem for derivatives, and the discussion about calculators and how you could fold the calculator or fold the difference quotient, and how some defects or limitations to using the calculator. All right, so an important concept in calculus involves different concept of differentiability. There are several definitions that you need to know. Differentiability at a point, on an interval, and just differentiability in general. At a point, a function of f of x is differentiable at x equals c is a constant, if and only if f prime of c exists. That's messy. F prime of c exists. Okay, so that basically the derivative has to exist there. That is, f prime of c is a real number, not an imaginary number, but a real number. Differentiability in an interval, similarly, it's differentiable on an interval a through b, if and only if it is differentiable for every value of x on that interval. So it's every single value of x, or every single point between a and b, open brackets, must be differentiable. It's open brackets because you know that at the endpoints we're only gonna have one-sided differentiability, not two-sided differentiability. The word differentiability in general is for functions. The function f of x is differentiable if and only if it is differentiable at every value of f in its domain. Okay, so it doesn't have to be differentiable everywhere in the world, but it does have to be differentiable in its domain. And so we've, on the previous slide or page, we've already listed the differentiable functions that are differentiable everywhere. Now, if we're talking about a piecewise function, you need to check all the pieces. Like if every piece is for example, if every piece is a trig function, or if every piece is a polynomial, all the ones that we said are already differentiable. If every piece is already differentiable, then we know the function is going to be differentiable as long as in between the pieces, or you could say at the endpoints of the intervals, where the pieces are joined, if those places are differentiable. But quite often, just like in our previous slide, if you have a piecewise function, this piece is differentiable, this piece is differentiable, but that interval, but right there at the junction, it's not differentiable. Oh no, oh yeah, right, because we have a corner, not differentiable. Again, this is differentiable over here, but this was not differentiable. Okay, so that often happens with piecewise functions. So the concept of differentiability in layman's terms means smooth. In your book, it talks about local linearity. So in layman's terms, if you, like we talked about the beginning of the year, if you zoom in and in and in on a differentiable function at a certain point, it's not even going to look like a curve or anything anymore. It's going to be linear, locally linear. Or in other words, it's going to be smooth, okay? A differentiable curve will have no sharp points in it, or cusp points, or places where the tangent line to the curve is vertical. Okay, none of our corners, cusps, jumps and holes. Imagine a train traveling on a set of differentiable tracks, and you will never get a derailment. That's a nice little analogy. Naturally, if a curve is to be differentiable, it must be defined at every point, and its limit must exist everywhere. What does that remind us of? Something that is defined at every point and the limit exists. Doesn't that remind you of continuity? So obviously, naturally, if so I'm told that I'm talking too fast. So if I'm talking too fast, go to YouTube and press settings and slow me down and play me at 0.5 or something. But I'll try to talk slower too. Okay, so differentiable. So if we're gonna, okay, so let's just read this. Differentiability implies continuity. This is very important, and it's very easy to get this mixed up. So to think the other way around. So that's why I'm pointing it out. Differentiability implies continuity. Continuity does not imply differentiability. It's not a two-way street. Oops. Okay, so you can, if you're differentiable, that means your derivative exists at that point. If your derivative exists, doesn't that mean that the point exists, the function value exists, and obviously the limit exists, right? But just because you're continuous, does that mean that you're differentiable? Does that mean that you have no corners, cusps, or jumps or holes? No, right? So let's look at each part. If a function is differentiable at x equals c, then it must be continuous. And actually, there's a proof of that in your textbook. It must be continuous at x equals c. So d implies, this symbol right here is the imply symbol. Okay, so d implies c. Or you can say, this actually is, if you remember from geometry, this is a conditional statement. Actually, it's not the imply symbol. I mean, we could translate that. This means if D, then C. If V, D, then C. However, if a function is continuous at x equals c, it need not be differentiable at x equals c. So if c, then d is not, simply not true. Okay? So it does not mean c, then d. And if a function is not continuous, then it cannot be differentiable at x equals c. Does anybody remember what this is called? We just negated. We took our original if d then c, and we flipped it around. We found the inverse. The inverse is c then d, but we negated not c then not d. That, my friends, is called the contrapositive, if you remember. And think about it this way. If I wake up early, then I will get a prize. The contrapositive is if I don't get a prize, that means I didn't wake up early. So, I don't know if that really made that much sense, but the contrapositive is always true. So again, if D then C happens, that means that if C didn't happen, D didn't happen either. So if it's not even continuous, don't even think about trying to be differentiable. Okay? So let's go on to the next slide. Oopsies. And try some of these examples. Determine whether the following are continuous. Okay? Differentiable, neither or both at the point indicated. So at this point, at x equals 3, x equals 1, 0, okay, etc. Okay? Okay, so at x equals 3, are we differentiable here? Well, first of all, let's talk about, are we continuous? No, right? Because we have a jump. If we're not continuous, can we be differentiable? No, ma'am. So it's neither. B. Okay, are we continuous here? No, ma'am. We have a hole, and so again, it's neither. Okay, are we continuous at x equals 0? Yes, ma'am, we are. Or sir, we are. We are continuous. I don't have to pick up my pencil. The limit from the left and the limit from the right match. The limit exists, and it equals the function output. Are we differentiable? Do we have any corners, cusps? Well, non-differentiable. Corners, cusps, jumps and holes, vertical tangents, asymptotes. So we have none of them. So we have both here. This is a winner. Okay, right away I can see there's going to be a corner, but is it continuous? Yes, it is. The limit exists and matches and all that good stuff. So it's continuous only. All right. What about here? I see an asymptote. So it's not differentiable, which means it's not differentiable. Is it continuous? No, because we have a, I guess you could say an infinite asymptote. So this is neither. Okay, here we have a corner, but it is continuous. Here we have another corner, but we are continuous here. And here we have, a vertical tangent, if you could see that. But it is smooth, it is continuous, not smooth. Okay, now let's see, next slide. Okay, this is getting longer than I expected. Now we're doing the same thing by looking at the the functions. So this is a polynomial function which is continuous and differentiable everywhere. Polynomial functions, remember, are continuous functions. So, well, not everything, everywhere. This is a rational function, so it's continuous everywhere in its domain and differentiable everywhere in its domain. But what is not in its domain is x equals 3, so it's not continuous at x equals -3. Now keep in mind this is still a continuous function and a differentiable function. So because in order to be such, all you need to do is be good on your domain. But if I were to ask, where is it not differentiable or not continuous, I'll tell you there. Okay, sine is continuous in its domain, which is all real numbers, so it's both everywhere. Hope you understand that. And this one is not continuous, although it is, let's see. Or maybe I should, at x equals 0, there's a dot there, and so, oh my. If it's not continuous, don't even think about it being differentiable, so neither. Oh my. Remember, there's a hole there. All right. Now, for the sake of time, and I have to go somewhere, I'm not going to do every problem. Actually, I didn't do it either last year. I'm not going to do every problem here, but I am going to, oh my goodness, I just realized I need to leave. Oh, okay. I'm going to stop right here. I'm going to post this and try to finish the rest after church today, okay?